Okay, now we are in the next part, and still we are in the learning the basics of this current electricity. And you might have come across all these basics when you were in your 10th class. And anyhow, we go for one more time into it. And here we will, in this session, we are going to talk about this or understand about this Ohm's law. So here, Ohm's law. What is this Ohm's law? Immediately, if I say the Ohm's law from your previous knowledge, you just remember it as V proportional to I. So how to just give the statement for it by understanding V is proportional to I. So here, if a conductor is there and if you are applying a potential difference of V across its end, the potential difference of V is applied across its end and the current I flows in the conductor. So now here, basing on this, how can we give the statement for the Ohm's law is when potential difference is applied across a conductor, then current in the conductor is proportional to the potential difference applied. So this is the statement. That means whenever you are applying the potential difference across its ends, the current flowing in the conductor is directly proportional to the potential difference applied, and we just show it as V proportional to I. Okay, after getting this from the Ohm's law, you can just make this expression as V is equal to some constant. Here the constant is R and it is I. What is this R means? It is the constant of proportionality. And this constant of proportionality is nothing but it is resistance of a material. So resistance of a material. And V is equal to R. But we remember this as V is equal to IR. So just keep in the mind as V is equal to IR. So R is the constant of proportionality and it is nothing but resistance of a material. And after understanding this, we'll talk about the materials which will be obeying Ohm's law and some materials which do not obey the Ohm's law. Suppose if you consider some materials which are obeying Ohm's law, they are called as ohmic conductors. And for these ohmic conductors, as V is proportional to I, if you draw a graph taking I on x-axis and V on y-axis, because they are directly proportional to each other, we get a straight line passing through the origin. So we get a straight line passing through the origin. So here the graph is linear. So we can keep another name for this as the ohmic conductors, otherwise called as linear conductors. An example for this is metals. Most of the metals obey the Ohm's law. So the best example for this is the metals. And from this graph here, we just you find the slope of the graph. That means y-intercept by x-intercept, V by I. Slope of the graph, V by gives the resistance of a material. So, like this, we can talk about these ohmic conductors which obey Ohm's law, and the materials which do not obey Ohm's law, which do not obey Ohm's law, they are called as non-ohmic conductors. Non-ohmic conductors. And if we just draw a graph here, taking I on x-axis and V on y-axis here, the graph is not a straight line, it is a curved line. And by looking at this, we can say the graph is not linear. So we can call these conductors as non-linear conductors. And the example for these non-ohmic conductors are like thermistors. I'll tell you what are the thermistors. And next is semiconductors, semiconductor diodes, or we can call them crystal structures. Other one is vacuum tubes. Vacuum tubes, electrolytes. So like this we can say these are the materials, some of the examples which do not obey the Ohm's law. And talking about these thermistors, what are thermistors? These are the resistors which change with the temperature. And here one more thing here, we are talking about this Ohm's law here. Here there is a limitation for this. This V is proportional to I. That means the potential difference applied and the current are proportional at when the temperature is constant. When the temperature is constant. So we should not stop there just saying that the current is directly proportional to potential difference applied. We have to just continue this with saying that the temperature is, and this will be applicable when the temperature is constant, and mechanical strain also. As a strain, as you read in your 11th class, mechanical strain is constant. If the material is subjected to strain, then we can see the variation in the resistance. And at the time, sometimes we may not find the V is proportional to I. So like this, we talked about this, and thermistors, we are in the thermistors. So these are the resistors which change with the temperature. You might have seen these thermistors. When you see any electronic circuits, then you can see a small one, just like a bud, it will be there, and it will be like this, and like this. The colors may be like blue, black, or red, like this, and on this sometimes it will be written as PTC or NTC, like that. So these are used in electronic devices, and later when we are talking about these semiconductors and semiconductor devices, we will learn much about these thermistors there. So that is about these thermistors and semiconductors. These are the crystal structures. What are semiconductors like junction diodes? It is PN junction diode. And you know well about these LEDs, light emitting diodes. So these are the examples for these. And you know about these vacuum tubes and electrolytes. So these are the examples for ohmic conductors and non-ohmic conductors. And here a question for you here. Suppose if you are given mercury and nichrome wire, and next is something like aluminium, and torch light bulb. The question is, among these, which do not obey the Ohm's law? The question is, which do not obey the Ohm's law? Here, mercury obeys Ohm's law. Nichrome wire is an alloy, it also obeys the Ohm's law. Aluminium obeys the Ohm's law, and the torchlight do not obey the Ohm's law. Because here, tungsten do not obey Ohm's law. This is something what you have to keep in your mind. A good question over there. And coming to this V, talking about this V is equal to IR. Here R is the resistance of the material, and now next we will go with talking about this R. So now take a pause the video and take the screenshot of this. Okay, now we are going to talk about this R, resistance. By the name itself you can understand the resistance. Resisting. What does it resist here? Here we are talking about the flow of charges. So the same thing we can apply there, and we can say that which opposes or which resists the flow of charges through it is called as the resistance. So first of all, this resistance is, this is the property of a material, of a conductor, which resists the flow of charges through it, and this resistance is a physical quantity, and we can measure it. So certainly it will be having some units. So here the SI unit of resistance is ohm, and it's denoted by the symbol omega, the Greek letter omega. And how to just define this ohm? How to define a ohm? Already you know from the expression V is equal to IR, R is equal to V by I. From this we can define ohm, and this resistance is in ohm, and this V is in volt, I is in ampere. And when this will be equal to 1, if this is equal to 1 and if this is equal to 1. That means, and the resistance is denoted by symbol that is zigzag line. So in a circuit we use this symbol for showing the resistance. And suppose if a resistance is there, and if you are applying the potential difference of 1 volt, and if the current flowing in the resistance is 1 ampere, it is 1 ampere, then resistance will be equal to 1 volt. So now when we are defining the ohm, we cannot actually define it as ohm directly. So here we just go with saying that the resistance is said to be 1 volt. When the resistance is said to be 1 ohm, if the potential difference applied across the ends of the resistance is 1 volt and the current flowing through it is 1 ampere, so then resistance is said to be 1 volt. We define it like this. So here from this R is equal to V by I, you can define resistance like this also. It is a ratio, isn't it? It is a ratio of V and I. So resistance is the ratio of potential difference applied across the ends of a conductor, potential difference applied across the ends of a conductor, to with what it is with I, to the current passing through it. Through it means in that particular conductor. So like this also we can define the resistance. So like this will be defining the resistance, that's the symbol, the SI unit, the definition of the ohm, and sometimes we'll be just using, instead of using omega, some bigger unit like kilo omega, that means 10 to the power of 3 omega, and mega, kilo ohm, mega ohm, it is 10 to the power of 6 omega also we'll be using when we're talking about the resistance. So this is about the resistance overall here. Now here, a small numerical is given, basing on whatever we have learned now and using the expressions what you have learned in the earlier sessions. So here, potential difference across the resistance of a wire of a resistance is 5 ohms across the resistance of 5 omega. That means the resistance of a resistor is 5 omega, and how much potential difference applied? 10 volt. Find the number of electrons, small n, how much, flowing through a conductor in 2 minutes. 2 minutes. So this is the data collected from that given numerical. And now here we just look into the units. 5 omega is SI, omega SI, but this is in some other unit. So we'll just convert into seconds. It is 120 seconds. So now I want to find this n. From where I can get the number of electrons? From the formula of the total charge. Total charge Q is equal to Ne. So from this I can extract it. So N is equal to Q by E. And we already know Q is equal to IT. Q is equal to IT. So just substitute here I, T and E. So in this I know the time, and we already know what is E. E is 1.6 into 10 to the power of minus 19 coulombs is the charge of an electron. So I have to find I, and then I can go with this problem. So now how to find I? Using this Ohm's law, V is equal to IR, I is equal to V by R. So V is, how much it is V? It is 10, and R is 5, so it is 10 by 5, it is 2. Current is ampere, 2 ampere. So now I am having I am having T and E. Now going for substitution, N is equal to, what is I? It is 2. What is T? 120. What is E? 1.6 into 10 power minus 19. So your answer is 1.5 into 10 to the power of minus 21. It's a number of electrons. So this is a simple numerical. So here we use the expression V is equal to IR for calculating this, and the previous expression Q is equal to NE and Q is equal to IT. So by this we can calculate that. Okay, now after understanding that numerical here, now let us talk about what are the factors that affect or that influence resistance. So this is an important question in your 10th class. What are the factors influencing R, resistance? There you have learned about one, it is the length of the conductor, and number 2, it is area of cross section. Area of cross section of the conductor denoted by L, denoted by A, and third one is nature of the material. Whenever the material changes, then the resistance also changes. Nature of the material. And here along with this we are going to add one more thing, that is temperature. Temperature. So these are the factors which are influencing R. So when the question is asked what are the factors influencing R, you have learned earlier the 3 factors, and now one more you have added here, that is temperature, that is length of the conductor L, area of cross section A, and nature of the material and temperature. And there you might have shown expression for this, how this length is influencing R. It is R is directly proportional to L. As the length increases, resistance increases. And as the area of cross section increases, resistance decreases. So R is inversely proportional to 1 by A. And nature of the material, there is an expression for that. Whenever the material changes, the resistance also changes. Temperature here shows the different variations. In some cases it increases, in some cases it decreases. So later we'll talk about it, about the temperature here. And here, when we talked about when we just the resistance definition, here why this or how this is resisting the flow of charges? That's the question arises usually in your mind. So here already we know the electric current is due to the flow of charges. This flow is not just like going through an empty tube. Already it is passing through the conductor, means the conductor is made up of the material means molecules means atoms. That means these free electrons will move through these atoms. So generally there you can imagine these free electrons, when they're moving through the conductor, they will be having collision with these atoms. So because of these collisions, certainly these collisions resist the free flow of charges, which gives rise to the resistance. So along with that, the impurities also show the effect. So like this, we can understand the resistance. And here some of the factors we have talked, and this, when the question is asked, you will just answer like this. Besides this, for your knowledge, there are factors like light and magnetic field that also influences the resistance. Light and magnetic field, they also show this influence. An example for this light showing the influence is selenium. When the selenium is exposed to light, then its resistance decreases. So the example for this is selenium. And magnetic field. Magnetic field also influences the resistance for certain materials. For example, here we can take the good example as the bismuth, Ba. When you place the bismuth in the magnetic field, approximately its resistance decreases by 50%. It's showing a good effect on, or a good influence on this resistance. So besides, these are the factors which we will be just knowing, which will be showing, and these which we have to keep in our mind. So these are the factors which influence the resistance. Okay, now pause the video and take the screenshot of it. Okay, here I will end the session with one more important thing here. So from these two here, R is proportional to 1 by A. Then you can write as R proportional to L by A. Already these things we have learnt. But anyways, just once again we are going through here. So now if you just equate with an constant here, R is equal to rho L by A. And this rho is the constant called as resistivity or specific resistance. Resistivity or specific resistance. Okay, now here, when you hear about this term specific resistance, in your 10th class you might have got a question. Suppose if a wire of certain resistivity is given for you, resistivity whose value is something like X is given, and if the dimensions of this material is changed, like if the length is doubled or if area of cross section is halved, what happens to its resistivity? There you might have learned there, it remains as X itself, even though if the dimensions are changed, it still remains as X. That means there you might have kept in your mind a point there. The resistivity of a material is constant. If you just take a copper wire and if you know the value of the resistivity of that resistivity, not the resistance, resistivity of that of the wire given for you, then if it is asked what is the resistivity of a copper vessel given for you with a certain volume, the same value, the resistivity of a material remains constant. Okay, later in the next session we'll talk about the complete about the resistivity, conductivity, conductance and all these things. Okay, and see you in the next session.